Hello dear friend, this is Himmet. The lecture 11. In this lecture we deal with the topic of the series. Okay, now suppose that k is an natural number, a sub k is a real number, then such an infinite sum is called an infinite series. Furthermore, the a sub k is called the general term of the given series. Okay, now as n equals finite sum from 1 to n, a k is denote the nth partial sum of the given series. Then we call Sn as an sequence and sequence of the series, which means that sequence of the nth partial sum of the given series. Now, if this sequence is convergent, which means that the limit of the sequence exists, then we call that our series is convergent, and at that time the sum of the series is S. Now, if the sequence S sub n is divergent, which means that the limit as n goes to infinity, S of n equals minus plus infinity, then the series is called divergent. Okay, now we have a theorem. This theorem say that the general term of every convergent series goes to 0. Right? You can follow the proof of this theorem from here. Now, but be careful that the converse of this theorem is not true in general. Let's give an example for this remark. Now, please examine the character of the given series. Now, the solution is like this. Let's write the nth partial sum of the series. Then S of n is finite sum like this, and then if we write the terms of the finite sum like this, we have ln 2 over 1 plus ln 3 over 2 plus ln 4 over 3 and so on, ln n plus 1 over n, and then we have such a expression. If we cancel similar terms, then we have nth partial sum of the series is ln of n plus n. Now this is a increasing function, and so the limit as n tends to infinity, s of n is equal to infinity. Thus the given series is divergent. But if we look at the general term of the series, then a sub k is ln of 1 plus 1 over k, and so the limit of the general term is 0. Namely, the general term of the series goes to 0, but the given series is divergent. This means that if the general terms goes to 0, then we can conclude that the given series is convergent. Now, from this example, we have such a corollary. If the general term of the series doesn't go to 0, then the series is divergent. Okay? For example, let's look at this series. Then the limit as k tends to infinity, a sub k equals 1, which is not equal to 0, then the given series is divergent. Right? Now let's give some example. First example is, what is the character of the series infinite sum from 1 to infinity 1 over k times k plus 1. Now, firstly, we have to write the anti-partial sum of the series. Then, anti-partial of the series is a finite sum from 1 to n 1 over k times k plus 1. If we look at the general term of this finite sum, then we have to say that by using the general chemical rule, that chemical rule say that similar solve the similar. Then let's write general terms 1 over k times k plus 1 is a over k plus b over k plus 1. Now here we are writing this expression as a partial fraction or simple fraction, and then we find that a is b and b is minus 1, and so if we put 1 instead of a and if we put -1 instead of b, then we have and partial sum is like this. If we write this sum clearly, and then if we write this sum clearly like this, then as you can see that we have similar terms. Then if we cancel similar term, for example 1/2, here we have -1/2, please cancel similar term, and then we have and partial sum S sub n is 1 minus 1/m plus 1. And so the limit of this sequence is, as you can see, that 1. So the given series is convergent. And so the sum of the given series is 1. Now, second example is, what is the character of the series? Now, as we did in the example 1, we need to write the general term as partial fraction. Why? Because we said that chemical rules say that similar solve and solves similar one, and so I think we can write this term like this as a partial fraction, and then anti-partial sum of the series is like this. And then again, if we cancel the similar terms, then we have that the nth partial sum S of n is 1 minus 1/n plus 1 factorial. And then the limit of the nth partial sum is 1. Then the given series is convergent again, and so the sum of this series is 1, which is the limit of the nth partial sum, right? Now let's look at this special example. This example actually give us a main information about the geometric series. Let's find the sum of the series infinite sum from 1 to infinity a to the k minus 1. Now, the solution is like this. If we write the nth partial sum of the series, we have nth partial sum of the series is 1 minus n to the n over 1 minus n. And so for 0 less than absolute value of a less than 1, then we have the limit as n goes to infinity, a to the n is 0, and also the absolute value of a greater than or equal to 1, then we have the limit as n tends to infinity, a to the n equals minus plus infinity or doesn't exist. Thus, we have such a situation. For this condition, the limit as n tends to infinity, s of n is 1 over 1 minus a, and so this geometric series is equal to 1 plus a squared and so on is 1 over 1 minus a. Now here, be careful, the first term is 1. For this condition, our geometric series is infinity, which means that our geometric series is divergent. For example, if we look at this series, the general terms, which is a n is 3 over 2 is greater than 1, and so this series is divergent. Right. Now, let's look at the example 4. Write the repeating decimal 0.12, 12, 12, and so on as a fraction in lowest term. The solution is like this. This repeating decimal can be written like this. Now we would like to this repeating decimal as a form of geometric series, so that the first term must be 1, and so here we get the 1, and so our a is 1 over 100, and so this is a convergent series which is equal to 1 over 1 minus a. If we put a is 1 over 100, then we have this repeating decimal equals to 4 over 33. Now let's look at the example 5. What is the sum of this series? If we use geometric series, then we can write this series as like this. Now again, if you remember the geometric series, first term must be 1, and then we have here first term is 1, and so this series is equal to this infinite sum, and so here our a is 1 over 2, and so if we put a is 1 over 2, then we have the sum of the given series is 1 over 4. Right. Thank you.